We're very happy to have Ali to give the second talk about on the effect of triadic closure on network segregation.
Okay, can you hear me? Okay, awesome. Hi everyone, I'm Ali, and I'm gonna present our work on the effect of triadic closure on network segregation. I'm gonna define these terms shortly, no worries. This is a joint work with Rediet, Nicole, John, who is here, and Brendan. Okay, we study heterogeneous networks here, where agents have types. That type might be a demographic group, for example. And here, different types are depicted with different colors. And the pattern we often observe in real-world settings is that there is a segregation between different types, which is harmful because it amplifies existing inequality. So the way we measure segregation is actually with the opposite term, network integration, defined as the fraction of bichromatic edges in the network, which are the edges between nodes of dissimilar types. Okay, one of the factors known to be responsible for network segregation is homophily, which says individuals have a tendency to form ties with whom they are similar to them. And because homophily is a natural force, it's actually challenging to push back against it. So we probably need to identify other social processes which are already amplifying or weakening homophily. In this work, we study triadic closure. What is triadic closure? We call such a structure a wedge, which we have two individuals not yet connected, and they have at least one common friend. And wedges might be monochromatic or bichromatic, depending on whether the missing edge is monochromatic or bichromatic. So triadic closure says that wedges are likely to be closed. That is, friends of friends are likely to be friends. And more precisely, wedges are equally likely to be closed. That means regardless of being monochromatic or bichromatic. Okay, and triadic closure is often cited as one of the factors amplifying homophily in the network. For example, this work by Kotsinis and Vass mentioned type formation is heavily biased by triadic closure, which constrained opportunities, or more recently, Asikainen and others mentioned that even a small amount of just homophily may be greatly amplified by triadic closure, or even more recent one. Social networks amplify inequalities by mechanisms like triadic closure. So we wanted to know, actually there is an intuition for all of these results, and the intuition is, let's say Bob is an agent in our network, and if there exists homophily, we expect Bob's friends to be similar to him. Here, 2/3 of them are similar, and so the friends of friends. So these friends of friends are actually candidate new friends accessible through triadic closure. And here, these candidate new friends, 2/3 of them are similar to Bob, which seems like that triadic closure is just replicating existing homophily. Here is the question, is this intuition complete? There is actually an alternative intuition. In the original intuition, we assume that none of the friends of friends are yet connected to Bob, but that might be the case. And in this case, still initial friends, 2/3 of them are similar to Bob. But if you look at the friends of friends here, which are likely to be friends through triadic closure, only half of them are similar to Bob, which means triadic closure is less biased. Now that's the important question, which intuition is correct? We think the original intuition is actually incomplete. And let's study this more mathematically. For example, in stochastic block models, here we have 3 types. The probability to have an edge between agents of dissimilar types is P, and the probability to have an edge between agents of, similar and this one dissimilar types is Q, and we say there exists homophily if P is larger than Q. So the question is, how would triadic closure affect network integration in stochastic block models? Let's say G is a realized network from a stochastic block model. This is how we define the effect. We close a random wedge and call the network G prime, and then measure the change of integration due to closing this random wedge. And given this definition, we have this fairly general theorem here. For any sufficiently large stochastic block models, triadic closure has actually positive effect on network integration if and only if there exists homophily, which is definitely surprising and against previous results. Okay, one might say that the effect you just observed is because network G prime has one more edge than G, but That's why we call this effect absolute effect and define another notion of effect to be called the relative effect. We consider a baseline mechanism that adds an edge to network G and call the resulting network G double prime, and define relative effect as the integration resulted from triadic closure minus integration from this baseline mechanism. The baseline we consider is actually a gamma homophilous random edge to be added to the network. What is a gamma homophilous random edge? We select a random edge, a random missing edge, but we weight up monochromatic edges by factor gamma larger than 1. And again, we observe that triadic closure can have positive relative effect on network integration if and only if this ratio of P over Q is bounded. And what determines those bounds actually depends on the network structure and factor gamma. And these bounds are monotonic. So yeah, the other way to say it is that the effect is positive if and only if the network is not very homophilous or very heterophilous. So far, I discussed the effect of triadic closure in stochastic block models, which are consistent, general, and against their intuition. So one might say that, okay, your results are very specific to your notion of integration. We don't think this is true because we use another notion, eigenvector centrality, and showed in a simple case of having two types of agents, triadic closure actually relatively improves the position of minority group. The other concern might be that maybe our results are very specific to stochastic block models. That's why we study a more complex model, Jackson-Rogers model, which is a dynamic model very popular in economics. Let me briefly explain what is Jackson-Rogers model. I'm going to explain it only for two types of agents, but our results are general for any composition. Okay, Jackson-Rogers model has two phases. In phase 1, let's say Alice is a new agent just arrived. She chooses NAS similar friends and NAD dissimilar friends. And in phase 2, consider immediate friends of initial friends. Alice is going to choose NAF from friends of friends, but this step is also biased. Alpha proportion of those friends of friends will be selected from friends of initial friends. Okay, homophily in phase 1 requires NAS to be larger than NAD. We can define homophily in phase 2, but it's actually vague, and I think because the results does not depend on alpha and does not depend on this definition, we don't need to define homophily in phase 2. So the question we want to study for Jackson-Rogers model is, again, how would triadic closure affect network integration? And unlike stochastic block models where we had to apply triadic closure post-network formation, here triadic closure is actually a part of the network evolution. This NAF, number of friends, accounts for triadic closure. So we define the absolute effect by measuring the network integration in equilibrium if we increase NAF while other parameters are fixed. One might say, again, you're increasing total number of edges, so we define this relative notion by, again, increasing NAF, decreasing initial friends, and measuring network integration. And no matter how you define this effect, we observe for any evolving Jackson-Rogers model, triadic closure has positive, absolute, and relative effects if and only if the first phase is homophilous. And to obtain this result, actually, we introduced another theorem which studies the expected behavior of the network after convergence. Here, we propose the integration of the networks goes to this quantity with this rate, interestingly, regardless of the distribution of the node types. And to prove this theorem, we require to do some mean-field approximation. Okay, so far I discussed the stochastic block model and Jackson-Rogers model, and we obtained counterintuitive results. But our results are not only counterintuitive, they are actually against a recent mathematical study by Esikainen and others. They also have a dynamic model. Let's say this is the graph. Bob is randomly selected to create a new edge. He has two options. With probability C, he will find a candidate neighbor by triadic closure, and with probability 1 minus C, he will randomly select someone to be friend. And depending on whether this new edge is going to be monochromatic or bichromatic, the probability that this edge is going to be formed will be S or 1 minus S. S here accounts for homophily, so if S is larger than half, we have homophily. And you might ask, why they obtained different results, we actually realized that they have added an extra layer of homophily to the definition of triadic closure. So we modified their models, and now we modified this bottom line. We have triadic closure without bias. This is how triadic closure is studied, and we have empirical evidence for that. And now we obtain consistent results. Again, if we increase these parameters, C in modified Asikainen and others model, and if, let's say, we have two equiprobable types, we will observe higher network integration, again, if there exists homophily. So far I discussed 3 different models, and we observed general consistent results. But theoretical studies often have some limitation. That's why we wanted to see if our results generalize to empirical case as well. So we studied the citation network where nodes are articles and edges are citations. And node type here is defined as the field of study. And the dynamic of citation networks is known to be captured by Jackson-Rogers model. That's because we have a directed graph, nodes appear sequentially, never disappear. And it seems that researchers find relevant works by a kind of 2 phases mechanism. So we wanted to test this theorem we had, which says integration in limit goes to this quantity. We can definitely measure integration from the data we have, but to see what is our theorem's prediction, we have to estimate these parameters from observational data, which is not at all straightforward. Consider this simple network here. I want to know which of citations from article U are created actually in the first or second phase, and you see there are 3 possibilities here. For example, all of them might be created in phase 1. Because we don't have any evidence which of them is superior, we assume all of them are equiprobable, and we estimate model parameters, but still this theorem only gives us a single number, and we cannot test it by a single number. That's why we cluster different fields of study and study each cluster separately. Now we will have 1 predicted integration per cluster, which means we will have more predictions. And because different fields of study have different norms, we have variation across our predictions, which is good. That's why we can do a stronger test. Let me briefly explain this empirical result. Our paper is actually theoretical, but this is just an empirical evidence. On the x-axis, I have observed integration from data, and on the y-axis, I have the predicted integration. And for each cluster, like electrical engineering, I have an arrow. It starts where the integration was in the beginning of the study and where in equilibrium integration ends. And ideally, we would like to see that our predicted integration in equilibrium matches with observed integration in equilibrium. And that's something we somehow observed. Except for 1 field, our predicted integrations are well matched with observed integration. We also did a counterfactual estimation, and it seems triadic closure is responsible for 3 to 5% of the network integration, which is significant. Okay, so far I discussed about the interaction of triadic closure and homophily, but one can leverage these results and intervene in the network. For example, the recommendation you receive from Twitter about who to follow is sometimes based on who is your current network following. That's actually the amplification of triadic closure. Or even in offline settings, a school board might recommend friends of friends to be roommates, which seems to be reasonable, and we now know that this will result in a more integrated campus. So I'm not going through details, but we study interventions acting solely based on phase 1 of the Jackson-Rogers model, and we provide some solution for short and long-term effects of interventions in this model. We also introduce the optimum interventions problem under some stability constraints when you want to maximize the integration of your network subject to some rate of change constraints. Okay, there are definitely other social processes that change the network. Their interaction with triadic closure is unknown to us. They might flip the sign of the effect we just studied. And there are definitely other measures of network integration beyond what we studied here that might be of interest in specific applications, I think. We studied optimal interventions for a very specific setting, but I think further studies are required both theoretically and experimentally to understand the effect of interventions in the presence of triadic closure. And finally, we relied on observational data to evaluate our theorem, but the best practice here might be to do interventional studies. And yeah, that's it. Thank you. I'm happy to take questions if any.
Are there questions from the audience in the room or on Gather?
Okay, no question.
Thank you. Let's thank our speaker again. Let's move on to the third talk.